Welcome to the third video in the Intro to Quantum Computing video series on multiple qubits. In the previous video, we introduced Mr. Qubit. We went over the concepts of what a qubit is, how we can describe it with the wave function and the block sphere, and what makes a qubit so special, particularly superposition. We also covered how to change its state using single qubit gates, which are just rotations of the block sphere. If you're unfamiliar with these concepts or need a refresher, click on the link in the description to watch the previous video. Now, the thing is that as exciting as one qubit is, we can't do much with it, just like we can't do much with one classical bit. One qubit represents just one unit of quantum information. So in this video, we'll talk about how we can represent and process more information in a quantum computer. In particular, we need a system of multiple qubits to store and process more information, to perform useful computations. Only then can we hope to realize the capabilities of quantum computers, such as factoring of large numbers, quantum simulations of chemical and biological systems, database search, and more. By the end of this video, you'll understand what a multi-qubit system is, how we can work with it, and why it is so useful. Let's get started. So, how do we represent a 2-qubit system? Well, recall that with one qubit we had two possible states, up and down. So, you can think of this notation as denoting one of the possible states that a single qubit can be in. Now, we have similar notation but with 2 qubits. What states can the system be in? Well, we still follow the same rules as before. Each qubit can be in either the up or down state, and so let's see the possible states that the system can take on. Both qubit 1 and qubit 2 can be up. Qubit 1 can be up while qubit 2 is down. Qubit 1 can be down while qubit 2 is down. And qubit 1 can be down while qubit 2 is up. And these are all the possible 4 states or measurement outcomes that we can have with 2 qubits. If we were to have a 3-qubit system, then we would have 8 possible states. For a 4-qubit system, then we would have 16 possible states. The number of basis states is 2 to the number of qubits, just like it was for classical bit systems. Now, numerically, up represents 0 on a block sphere, and down represents 1 on a block sphere. So we use the same notation as before. The up is denoted as 0, 0, up-down as 0, 1, down as 1, 1, and down-up as 1, 0. Alright. Further, the 2 qubits can be in a superposition of these possible states. The only constraint, as we had before with a single qubit, is that the sum of the probabilities must add up to 1 or 100%. We can write a superposition of these states in a wave function, more precisely called a state vector, just like before. Now, the wave function represents 2 qubits. We sum over the possible states, with the amplitudes of each being represented by a Greek letter like we had before. 0, 0 has alpha amplitude, 0, 1 has beta amplitude, 1, 1 has gamma, and 1, 0 has delta. We've added 2 additional Greek letters to represent the additional states that are possible. In reality, it doesn't matter which letter we choose to represent the amplitude of each. What's important is that we do assign one. Once again, the probability of the system being in each state is denoted by alpha squared, beta squared, gamma squared, and delta squared. See, so all of our notation is basically the same. But because we have 2 qubits, we have 4 possible measurement outcomes. The 2-qubit system represents more quantum information. Similar to before, we want to be able to operate on these qubits. We want to change the state of the system. And we can do this with another set of gates called conditional logic gates. These gates look at the starting state of a 2-qubit system and operate on conditional logic. If the initial state is such and such, then perform a certain operation. This is the same thinking as the classical conditional logic gates that operate on bits, except now with qubits. For example, a very important conditional logic gate is the CNOT gate, which stands for control NOT gate. The CNOT looks at the first qubit in the system, known as the control. If the control is in the 1 state, or down, then it flips the second qubit, which is known as the target. We can represent the CNOT with this symbol, where the top circle represents the control qubit and the bottom the target qubit. Let's say that our input state is 1, 0. The CNOT looks at our first qubit, the control, and asks, is this in the 1 state? If yes, then the second qubit, which is the target, is flipped, regardless of its initial state. In this case, the control is 1, so the CNOT flips the target. Note that the control qubit is never flipped by the CNOT, so our output state is 1, 1. We've changed the information stored in the qubit system. Let's say that we have 0, 0 as our input. Since we have 0 for the control, then the CNOT does nothing to the target, and we are left with 0, 0 as the output. The CNOT does not only operate on basis states, however. It can also operate on superposition states, and that's where things get interesting, as you'll see in just a second. What can we do with quantum gates? Why are they useful? Well, let's look at an example. Let's start with a 2-qubit system that is in the 0, 0 state. This is our input. Next, let's apply a pi/2 rotation on qubit 1, because remember, we can still operate on each qubit individually with rotations. And next, let's apply a CNOT gate to the 2 qubits. What output will this produce? This output is actually an incredibly counterintuitive and important state in quantum computing. We won't go into the math of how we get here, but instead let's immediately take a look at the output. It is 0, 0 plus 1, 1 over root 2. Notice the root 2 again? That means that we are in a 50-50 superposition of these two states, just like we had last time with the equal superposition. Except now, we have 2 qubits that would be found in the 0, 0 state 50% of the time, and in the 1, 1 state another 50% of the time. We also note that the coefficients for the 1, 0 and the 0, 1 states are 0, since they're missing from this expression. This means that there is no possibility for the system to be in the 1, 0 or 0, 1 states. So, the only possible states that these 2 qubits can be in are either both 0, which happens 50% of the time, or both 1, which happens the other 50% of the time. This type of state has a property so important that it is given a name in quantum mechanics: entanglement. This particular state is one of 4 possible Bell states, named after John Stuart Bell, who in the 1960s used these states to theoretically prove a very important theorem, Bell's theorem. His theorem is a bit too deep to get into in this video, but it shows that quantum particles can exhibit correlations that are stronger than any classical model of physics would allow, which is another way of saying that quantum mechanics is just plain weird, and can never be explained by some complicated classical theory in disguise. What is so important about entanglement? Well, in this state, if we measure 1 qubit, we will automatically know what the state of the other qubit in the system will be. How is that so? Well, remember that we are talking about 2 qubits that can be both 0, 0 50% of the time, or both 1, 1 50% of the time. So if we make a measurement on qubit 1 and we see that it is in the 0 state, then the only state that has 0 for qubit 1 is 0, 0, and therefore we know that qubit 2 must be in the 0 state. In contrast, if we measure qubit 1 to be in the 1 state, then the only state that has 1 for qubit 1 is 1, 1. Therefore, qubit 2 must also be in the 1 state. This is incredibly useful because now, if you think about this computationally, this allows us to create a relationship between two qubits that is stronger than any correlation that is possible in classical physics. These kinds of correlated states are simply not possible in classical computers. This opens doors to different types of computations than we see today, because just like the property of superposition, entanglement breaks through the physical limitations of classical computers and allows us to explore new frontiers, new ways of building algorithms and computational models. This just keeps getting curiouser and curiouser, doesn't it? But remember, qubits don't have to be entangled with each other. Only certain multi-qubit states contain entanglement. We did this whole set of operations to get there. However, the fact that qubits can be in superposition allowed us to get to entanglement. And now, we have another tool in our quantum computing toolbox. So let's sum up this new curious phenomenon of quantum bits. First, in the last video, we said that we have a single qubit that is represented by the block sphere. And we can change the state of this qubit by rotating it in any direction we like, using rotational gates, such as a 90-degree rotation. These rotational gates allow us to operate on single qubits and put them into superposition states. Second, now in this video, we showed that we have gates that operate on systems of multiple qubits, since we can't do much with one qubit alone. Gates that operate on multiple qubits are called conditional logic gates, such as the CNOT gate. And in combining rotational gates and conditional logic gates, the phenomenon of entanglement naturally occurs. And lastly, with all of this hard work put into understanding superposition and entanglement, both of these properties allow us to finally be able to accomplish the problems that lie in this outer circle, the oh-so-mysterious and desirable quantum information processing circle. The quantum information processing circle will allow us to do both classical information processing computations, but also computations that are very difficult for classical information processors to do today in a reasonable amount of time, such as quantum simulations of molecules or factoring of large numbers in polynomial time. If we were to try such computations with a classical computer today, it would require immense computational power, and we might not even have an answer for many years to come, as the computer takes its time to crunch the numbers. But the hope is that once a quantum computer with enough qubits and good enough error correction is built, we'll be able to solve many hard problems much more rapidly, or in polynomial time to be exact, which means that the total computation time is a polynomial function of the problem size. Virtual or telepathic high five, everyone. That was a lot to cover. So now that we understand the basics of how quantum information processing theoretically works, one question remains. How can we realize these qubits in real life? To create a qubit, we know what we need to do. We need a quantum two-level system that can be in the up and or down states, be in a superposition of these states, and can also be entangled with other qubits. Is there even a particle like this that exists in real life that we can use as a building block for a quantum computer? Well, curious viewer, I'm glad you asked. Tune into our next video to see how a mysterious particle property called spin will allow us to realize qubits in real life. This video was written, narrated, designed, and musically composed by Romi Lifshitz. Thank you so much to Professor Jonathan Baugh from the University of Waterloo's Institute for Quantum Computing for his immense support in making this video. The Baugh Lab is working on exciting physical devices that will enable quantum information processing. To learn more about their amazing work, be sure to check out the link in the description and tune in to the next video.